Hey, it's Tyler with Deepcode, and in this segment, I'm going to be talking about design by contract. I'm going to explain what design by contract is, and I'm going to walk through some code that I wrote showing design by contract used in practice. So when we're constructing software, what we want to be aiming for is to provide functionality to end users that end users can use confidently without having to read our source code, without having to read our implementation. In other words, we basically want thorough and correct interface documentation. And design by contract is a software construction practice that helps formalize interface documentation, and it helps boost the ability for people to use software confidently by just reading the interface specification. So design by contract introduces the concept of preconditions, post-conditions, and invariants to interface definitions. A little more formally, design by contract describes requirements on the runtime state before entering your functionality and what the state of the runtime looks like after your functionality returns control flow back to the caller. And it also prescribes some expectations, some requirements on the data coming into your functionality and the data coming out of your functionality. So basically input arguments and output values. I like to think of preconditions and postconditions as describing the requirements on the runtime state, and invariants describe properties of the input and the output data. So I'll show some code here. Let's pretend that we're going to build some library called foo, like the foo library. So this is just a header file. Design by contract is concerned mostly with the interface definition, so we're not going to look at implementation today. I'll just go through the file section by section. So at the very top, you have your header guard, of course. Then you have some toy documentation for your library. We introduce a data type here called foo resource. Because it's a toy example, I didn't document it. And we don't actually need to have any fields inside a foo resource, just have something to suggest that we can transact with a specific data type from our library. And we're going to pretend that our library requires initialization before the user can use any other functions in our library. So we provide this function called foo init. And foo init says, as it says, it initializes the foo library, and it must be called before using any other foo functionality. And then we document the return value. We don't have any pre or post conditions here for the runtime. This second sentence here might sound like a precondition, but in the case of design by contract, pre and post conditions describe the runtime at the interface to your functionality. And so this is basically just a general usage statement about our library, saying if you want to use features from our library, you basically need to initialize our library with this function first. So I don't want to be pedantic here, but I will show later on what an example of a precondition looks like. But here we do have some guarantees that we put on the output value. So we say the output value from our functionality is going to be true if initialization succeeded, or if the library is already initialized. Another way to think about the latter part of that statement is this is documentation that covers what happens if foo init is called multiple times. Otherwise, it returns false if initialization failed. And if it's called multiple times and it failed the first time, for the sake of the toy example, we just assume it keeps failing, so it'll keep returning false. Now, after providing init, we have another function here called new foo resource. And this new foo resource, the interface is a bit contrived. You would probably have a simpler interface that simply just returns the pointer itself, null or non-null. But for the sake of the toy, I've made it a little bit contrived to demonstrate design by contract. So this interface here, the signature returns a bool, and we document the return value here, and it also takes as input argument a pointer to a foo resource. So going top down from the documentation, we have the typical explanation of what, in this case, a simple explanation of what the function does. So we use this kind of as a factory function to create a new instance of a foo resource. And here we explicitly call it preconditions and postconditions. The precondition is that foo init must have been called, and it must have returned true. So this is another way. This is an explicit requirement on what we kind of implicitly implied for the rest of the library up here. Basically, it must be called before using any other foo functionality. And the post condition here is that the caller is responsible for the memory of the allocated foo resource. Now, even though this is describing it's describing the instance of the foo resource, it's not actually a property of the returned foo resource itself. Instead, it's a caller's responsibility. And so this one's a little bit of a stretch for a post condition, but we do, this is a C example, and C doesn't provide language features to suggest memory ownership. So we do have to call out who owns the memory and who's responsible for it. And then we come down here to the parameter documentation. Again, this is where the invariants are going to be. And so using this kind of JavaDoc or Doxygen style markup, we have an output parameter, and we say that fr, short for foo resource, is a pointer to a foo resource. And now we place some invariants on this, some expectations and requirements. We say that foo resource itself must not be null. That's basically another way, or the reason we would say that is because hypothetically we're going to modify what this thing points to on the caller side, and it's going to point to, later the documentation will say that it's going to point to a usable instance of a foo resource if everything went well. So it can't, the pointer can't be null, because then we can't dereference it. Now, the dereferenced pointer must be null, and this is assuming that, again, we're going to overwrite the value of the caller side pointer to point to a usable instance of foo resource if everything goes well. And so if the caller side pointer already points to something else, we don't really know what to do with that memory on our side. And so we would probably leak it if, assuming that was an allocation, we would leak it when we change its value. We don't actually know if we'd leak it or not. I mean, maybe the caller actually has another pointer pointing to that same space in memory that they're going to clean up. But basically, this is our way of saying that we don't take responsibility for whatever this thing used to point to. Now, again, the dereferenced value, the dereferenced fr argument, points to an instance of foo resource that's ready for use if the function succeeds. That's the success case. And then the failure case is that it points to null in the case that the function fails. As this is a toy, this doesn't go as deep as possible. Depending on the context in which you're writing software and who you're providing it to, you can go much deeper than this, or you can go a little bit shallower. That's mostly depending on whether or not we're talking about like a safety critical system or something that's more just a desktop application, to handle photo processing or something like that. So for example, the ways we could go deeper are talking about thread safety. For example, what happens if you call foo init once in one thread and then another time in another thread? They get called at the same time, for example, or around the same time. What happens then? And you could also talk about reentrancy, for example. What happens if one thread calls foo new resource and then gets preempted halfway through, and another thread tries to enter foo new resource while the previous thread is suspended? Is that a legal program state? Can your library handle that? These are the sorts of things that we can go into. And the last thing to talk about with design by contract is if we were to actually provide an implementation for this, as the authors of the implementation, we have a choice for whether or not we actually want to assert on our preconditions, postconditions, and invariants, at least the ones that we have information sufficient to assert on. For example, the postcondition here, we can't actually assert that the caller cleans up the memory because that would happen outside of scope of our library, and we just don't have visibility into that. However, we could add runtime asserts on whether or not the fr value is not null and the dereferenced value is null, and things like that. In general, if we don't add asserts, then we kind of leave things up to the human level for the caller to keep track of whether or not they obeyed the contract. And bugs can slip into programs then when you essentially violate the contract, but we don't give an indication that it was violated. So oftentimes it pays to raise errors or assert or something like that when your contract is violated. And that's an example of design by contract. Design by contract is, once again, it's a way of formalizing your interface definitions by introducing preconditions, postconditions, and invariants. And what it helps achieve is allowing your end users to use your software with confidence by just looking at the interfaces and not having to bother with the implementation.